Welcome to this screencast. We'll do all of chapter 5 like this. The first section is antiderivatives and indefinite integration. The objectives are the following. Write the general solution of a differential equation, use indefinite integral notation for antiderivatives, use basic integration rules to find antiderivatives, and find a particular solution of a differential equation. A differential equation is basically the equation we have after we've taken the derivative. So we are now looking at the opposite idea. Given an equation, how can we find the original function? We'll revisit these objectives at the end of this note. The first definition is a function capital F of x is an antiderivative of f of x if capital F prime equals f. So here we see how antiderivative is the opposite of derivative. All antiderivatives of f of x differ only by a constant, and this is y. If you take f of x equals x squared plus 5x minus 3, or f of x equals x squared plus 5x plus 1, or f of x equals x squared plus 5x plus 7, etc., any of these functions has a derivative f of x equals 2x plus 5. Therefore, if we're looking for the antiderivative of f of x equals 2x plus 5, we don't know which one was the original capital F function. But we do know that all of these capital F original functions differ only by a constant. In my three examples, the constant is negative 3, plus 1, plus 7, but there are obviously an infinite number of possibilities. Let's see some definitions now. F of x, the function we are trying to integrate, is the integrand. In this example, x is the variable of integration, capital F of x is an antiderivative, and c is the constant of integration. We've inherited this notation from Leibniz, the German mathematician. This sign here, which we see here, is actually a stylish capital S, and it stands for the German word Summe, which in English is just sum. So an integration is an infinite sum. So let's try to find the antiderivative of f of x equals x plus 1 over root x. We just substitute f of x, and we get the integral of x plus 1 over root x dx. We can break it down into two terms. X over root x is simply root x, and 1 over root x is x to the power of negative 1/2. Now, by thinking backwards with everything we've studied in chapters 4 and 5, we can figure out what function would have this as a derivative. Likewise, we can figure out what function would have this as a derivative. And the answer is 2 over 3 x to the power of 3 over 2 minus 2 times x to the power of 1/2. And then we have this plus c, the constant of integration. Be careful with the variable of integration. Here it's x. If it happened that the variable of integration was something else, for example here it's t, then suddenly all of this has to be considered as a constant. And if we integrate this now, we'll get x plus 1 over root x times t. X plus 1 over root x has to be considered just a number, and therefore it's x plus 1 over root x times t. Once again, we have a constant of integration. You may want to remember this formula here. If you're looking for the integral of a monomial x to the power of n, for example x to the power of 7, then the integral is going to be 1 over 8 times x to the power of 8, plus the constant of integration. Never forget that. Let's see a short example. If f of x equals x minus 1, that's a line. We could sketch the curve whose derivative is that line, and you probably have guessed already that it's a parabola. If we want to do that algebraically, capital F of x is the integral of x minus 1 dx. You can break down into two terms, the integral of x dx minus the integral of 1 dx. The integral of x dx, either by using the formula above or just by guessing, which I prefer, it's half x squared, and then the integral of 1 is simply x, plus c. So here's an example of an integral function. The derivative of this blue parabola would be the red line here, but we can realize that this second parabola has the same derivative, and actually there are infinitely many parabolas whose derivative would be that line. So this is what is represented by this plus c. It's a vertical shift, and this is what we call the constant of integration. If we are given a specific point, if we want our integral to go through a specific point, then we can find the particular solution. Here I have a point, and therefore I can find which of all the parabolas goes through that point. Another example here, find the general solution of the integral of 2 over cube root x dx. I'm going to write this as 2 times x to the power of negative 1/3. You can either guess or apply the formula, and you'll find 3 times x to the power of 2/3 plus c. Now, we can find the particular solution using the initial condition f of 8 equals 3. F of 8 equals 3 means 3 times 8 to the power of 2/3 plus c equals 3, and if I solve, I find that c equals negative 9. Therefore, the antiderivative is f of x equals 3x to the power of 2/3 minus 9. Many more integrals can be guessed. Since the process of integrating is the opposite of differentiating, many integrals can be guessed. For example, the integral of sine x dx, we think for a minute, and we find that it's negative cosine x plus c. If I take the derivative of that, I will find sine x. Same thing here, what's the integral of cosine x dx? We think for a minute, and we find it's sine of x plus c. What's the integral of e to the x dx? Well, it's e to the x plus c. This last example is a little bit more difficult. The integral of sine of x over cosine square of x dx. We need to reorganize this. It's 1 over cosine x times sine x cosine x, sine x over cosine x, which is secant x tan x, and you might remember that the derivative of secant x is this. Therefore, the integral of that is secant x plus c. So let's go over the objectives again quickly. Write the general solution of a differential equation. So we found that with this example. If f of x equals x minus 1, then capital F of x is half x squared minus x plus c. We have seen how to use integral notations for antiderivatives. We have seen how to use basic integration rules to find antiderivatives. For example, the integral of sine x is negative cosine x. And finally, we've learned that if you are given a particular solution, you can find the specific value of c.